Okay, folks, after having reviewed Frost, this is it's a short implementation of the key generation algorithm, and we're going to use it to create a multi-sig address for Ycash. So it's only one file actually. So if you remember, the key generation in Frost is a multi-party process. So it's a distributed key generation, and so it works like that, like this. But we have a test here, right? So in the test here, we are doing 2 out of 3 multi-sig. We need a random number generator, and for reproducibility, chose a reseedable random generator, cha-cha-20, and I set the C to be 0, so every time it would produce the same sequence. But normally you would use OS or RNG or thread RNG. So what do we do here? We have 3 participants. So we're going to call the function makeShare 3 times. The first parameter is the index of the participant from 1 to 3. T the threshold. So it's a 2. So there are 3 participants, but 2 signers will be only 2 signers will be needed. So it's a 2 out of 3, and then this is our RNG. Okay, so let's go to makeShare. This is makeShare. Each participant picks a secret, so that's like in the paper. That would be the A0 of our polynomial, and the rest of the coefficient. The polynomial has t is of order t minus 1, so it has the t coefficients. So it goes from 0 to t minus 1. Actually here you will see, you notice there's actually t minus 1 coefficients, because the secret is one of the coefficients. So this is actually A1, A2, A3, and A0 is our secret. Let me see if I can pull the wow, it's pretty big. Frost this one. Okay, why is lows? Alright, so that is, where is it? Key generation, I'm getting here. Right, so this is our polynomial where AI0 is our secret, and the rest, so going to t minus 1, are the other random coefficients. Let's go back here. So what do we do is we randomly pick them up, right? And finally, the share is the evaluation of this polynomial at coordinates 1 to n. And to do this evaluation, we use Horner's algorithm. So Horner algorithm is simply to say that if you have something like x cubed 2x cubed plus x squared plus 4, you refactor this as 2x plus 1 times x plus 4. So you basically do a multiplication by the coefficient, and you add you add the next coefficient, you multiply by x, you add the next coefficient, you multiply by x. So it's at the end, the latest term, the highest term, is the one that you push first, and the loop is multiplying by x and adding the next element. So this is exactly what's going on is doing here. We start at 0. We have reversed the the index, so that we pick up the highest coefficient first. We add it and we multiply it by x, and x is going to be 1 to n. So this evaluates the polynomial at 1 to n. Each time we do this, one evaluation of the loop gives us one evaluation, and then the return is we add the secret, because this doesn't evaluate the first a0. It evaluates a1 times x plus a2 times x squared, but not a0, so we have to add a0 here. And finally, our share is just the value of the, right? So we have this, where is it? Where is it? Yeah, this is what we're doing. We did that part. So one thing to notice too is that I skipped this part. I skipped the part where we are committing to a particular. I omitted this because basically this is for protecting you against replay attacks and against participants that ill behaved. The assumption here is that when you are doing this, we are doing this with people who want to participate and don't want to participate correctly. So this I skipped this 2 to 4. So this verification is also skipped. All right. So what I do have is I have these shares. So I and fi of L is going to be this guy here. At the end, calling this function make share with we use the 1 to 3. We give us 9 sets of DKG. Wow, 9 DKGs. Okay, so that's what's going on here. All right, that's what's going on here. So each guy gives us one set of 3 shares. So participant 1 creates 3 shares, 1 for himself and 2 for the other guys, and same for participant 2 and 3. And then I have written this function that simply serializes DKG data. You can see here the right function for DKG data is this guy. I write out the secret into a file, but that's actually not needed. This is for testing. Normally you don't want to do that. You actually want to throw you don't need a secret to sign. And then, but you need to use that secret to create your share of the public key. So that's the part where this is the first commitment. This term here is AI0 times G. The other ones of our verification of the protocol is followed properly, but that one is needed. So this term is going to be put into a file public, and then also we write all the shares. So at the end of running this function, this test function, right, what you get is so this is for the user 1. He would have this guy. So again, this guy is not needed. But just anything goes wrong, I can use this data to reconstruct the secret. But supposedly you are not going to use that. And then you have 3 shares. And then user 2 has created this guy, and user 3 has created these guys. Now there's a part where each participant exchange exchanges these files around. So normally at the end, you would have each participant has all the public shares. He has his own, right? But he gets a copy of 2 and 3. And for the shares, it's the exchange is such that user 1 will receive the shares one from the other guys. So you see you see that it's actually vertical. The user 1 has created this one, and this one. And user 2 has created this one, and this one. And user 3 has created this one, and this one. So the first number is the guy who creates the share, and the second number is the guy who should receive the share. So after the exchange, user 1 should have these 3 files. And user 2 should have these 3 files. And user 3 would have these 3 files. So what I've done is I've copied these files around into a directory, 1, 2, 3. And then in one, I have 1, 2, and 3, right? 1, 2, and 3. So that's just a copy of these files. Then in the next phase, so the second phase of the second round here, we calculate our long-lived private signing share by summing these guys together. So that's the step here. I could collect, and in collect, I call collect DKG. So collect DKG is the second function, right? Make share was the first one, and then we have collect DKG. So the collect DKG is going to open. So here's a file here. Read public share. So this is going to open the public file. So we have public 1, public 2, and public 3, right? So this is going to open the file public 1 for this guy. So you get the prefix, which is in this case the prefix is just a way to differentiate different runs of this program. Every time I have this is a prefix basically. So this opens the test public 1 with the index, and it reads the point that is inside, right, and then it returns it. So you can look at this file. This is just a series of hex numbers that corresponds to the u coordinate of our point. So what it does is it reads this guy, and then it turns it into a point on the curve. Initializes it as a point on the curve. Then the collect function does this for every public file, 1, 2, and 3, and simply sums them together. So all the points are summed together, and it's returned as our group public key. So that's what collect here does. So at the end here we have the public key, and this stuff here, the rest of the function, is some manipulation, so that we can create a full extended viewing key out of that. So extended viewing key has other information like the nullifier key and the D key. What was the name again? I got a lapse. Diversified key. These are not relevant for our purpose. So the trick I'm doing is that I'm creating a random viewing key. So to create a random viewing key, I actually create it from a random spanning key. So create a seed fill it with random bytes, derive a spending key out of that, and then get the extended full viewing key from that spending key. And now there's this Ycash function. This is the only function actually I have added to libbrus Ycash. This allows me to switch the public key that is contained inside this extended full viewing key. So A stands for authorization. So it's actually our public key for spending. So I set it there to be. So I'm basically rewriting a part of this full viewing key. And finally, I'm running this as an extended full viewing key to the console, and I'm getting the default payment address out of that. So the outcome here would be a viewing key and an address. So if I run this function now here, this should give me a full viewing key and an address. So the next step is to take that viewing key, import it into Y wallet. So for that, you can go to a QR code generator. Then you I put this guy in there. Sorry, this guy in there. This guy in there, I said. YURL. Free text. And then I use Y wallet to create an account and scan this as a full viewing key. The address that the wallet should give, it should be this address. It will be this address. Then the next step is to put some money in there. So I'll make a transfer of a little bit of Ycash, and in the next session, we're going to spend from it. Alright, so this concludes the first part, which was the creation of the multisig. So essentially, what the next step would be is that we use the cold wallet feature of Y wallet to spend from this address or this viewing key, for which we don't have. Obviously, we don't have a spending key because it's not going to be it's not a regular spending key. So as far as Y wallet is concerned, this is a cold wallet. So it is gonna save the transaction, all the nodes that are involved in the transaction, but it will not be able to sign it, of course. And then I would take that transaction file and do the same thing here. So I would this time or next time, obviously, we are going to work with the shares. As you can see, we haven't done anything with the secret shares. We only derived the public key so far. So in the next session, we are going to use the shares. Each participant or two participants out of three. We don't need three of them. We need only two. Two participants will use their signing shares to sign one part of sign their transaction and provide their share, the signature. And then these will be aggregated by any participant, and to produce a final signature. And that signature will be a raw file that we can transfer back to Y wallet and broadcast to the network. So essentially, what we're gonna have is a multisig cold wallet. All right. So until then, I need to obviously I didn't write the code yet, so that has to be written. All right. I hope it was interesting. I think it's quite interesting for me, at least, to learn this. All right. So see you then for the next part.